Hello students, welcome to this session. In the previous video, on power series solution of a differential equation, we have discussed how to find the series solution of Bessel's differential equation and some differential equation which can be reducible to the standard Bessel's equation. Now in this video, we study some of the properties of Bessel's function, and the first one of that one is Jn of minus x equals to minus 1 raised to n into Jnx. Now by the definition or by an expression for Jnx, we have Jnx equals to summation r varies from 0 to infinity minus 1 raised to r divided by r factorial into gamma of n plus r plus 1 into x by 2 raised to n plus 2r. Now in this case, we want an expression for Jn of minus x. Wherever x is there, now let us replace that x by minus x. Then we are going to get this expression. Now, just to consider this one, rest of the things remain same. Wherever x is there, we have replaced that one by minus x. Now let us consider this one separately. And let us join after replacement x by minus x, whatever we get, let us join it as equation 2. Now let us consider this minus x by 2 raised to n plus 2r separately. Then by the property of indices, a into b raised to x can be written as a raised to x into b raised to x. Accordingly, this one can be written as minus 1 raised to n plus 2r into x by 2 raised to n plus 2r. Again, this minus 1 raised to n plus 2r can be written as minus 1 raised to n into minus 1 raised to 2 plus minus 1 raised to 2r, because when the base is same, by adding the powers, we get our previous step. This we have kept as it is. And again, this minus 1 raised to n is kept as it is. This minus 1 raised to 2r can be written as minus 1 raised to 2 whole raised to r into x by 2 raised to n plus 2r. And that is minus 1 raised to n. This is minus 1 raised to 2 is plus 1 raised to r into x by 2 raised to n plus 2r. And 1 raised to r is going to be 1. Therefore, we get this one as minus x by 2 raised to n plus 2r equal to minus 1 raised to n into x by 2 raised to n plus 2r. Now, in equation 2, in the place of minus x by 2 whole raised to n plus 2r, let us replace that one by its equivalent, that is minus 1 raised to n into x by 2 raised to n plus r. We are going to get this particular expression. Now, this minus 1 raised to n is free from r, which is a parameter of the summation. By taking outside, we are going to get this thing. And according to equation 1, this is our Jnx. That's why we have proved that Jn of minus x equals to minus 1 raised to Jnx, because after taking this minus 1 raised to n outside, we get this particular expression, and that is nothing but according to equation 1, equation number 1, it is our Jnx. That's why this can be replaced by Jnx. That's why we have proved Jn of minus x equals to minus 1 raised to n into Jnx. That will be the first property on that Bessel's function. Now let us go for the second one, and that second one is Jn of j minus n of x equals to minus 1 raised to n into Jnx. And again, in both the cases, RHS is same, only there will be a change in the LHS. Therefore, now by the definition of j minus nx, we have this particular expression that we have proved while discussing the series solution of Bessel's differential equation. And j minus n of x equals to this minus 1 raised to r is written as it is, this r factorial is written as it is. Now this minus n plus r plus 1 can be written as r minus n plus 1, and this we kept as it is, that is x by 2 raised to minus n plus 2r. And from the first sem, when we studied the properties of gamma function, one of the result is gamma n plus 1 equals to n factorial when n is a positive integer. And just we can take use of this particular property here, this gamma of r minus n plus 1 can be written as r minus n factorial. And rest of the things are kept as it is, and let us do it as equation 2. And here you have to note down the limits carefully for r. In the previous case, the previous step, r takes the values from 0 to infinity, and in this case you have written r varies from n to infinity, because until r takes the value n, this expression leads to a factorial of a negative number, which cannot be defined. That's why here our r varies from n to infinity. If you take r equal to n, that is 0 factorial, we can define it as 1. If we take the next one, r equal to n plus 1 here, that becomes n and will get cancels 1 factorial, that can be defined. That's why here from this to this, the important thing you have to note is that here the limit of r varies from 0 to infinity. Here it varies from n to infinity, as I told, until r takes the value n, this number or this expression results in a number which results as factorial of a negative number, which cannot be defined. That's why r varies from n to infinity. Now let us take some substitution here. Let us take r minus n, this quantity equals to k. Accordingly, I can write r equal to n plus k, and these are the limits for n. Now we have taken the new parameter k. Let us take an expression for our limits for k by taking first, when you take the lower limit for r, that is n, then k results in 0, because if you take r equal to n, that is n minus n results in 0. If you take the upper limit for r as infinity, okay, that becomes infinity minus n, again that becomes infinity. Therefore, now equation 2 reduces to LHS is j minus nx, and that one equals to summation k varies from 0 to infinity, and this is minus 1, okay, raised to r is there, but r is n plus k. And again r is there, that is n plus k, and factorial written as it is. And since you have taken r minus n equal to k, that becomes k factorial. Then x by 2 as it is, this minus n as it is, plus 2 as it is. Again r is there, but r is n plus k. And now this j minus nx, that is LHS. Now this minus 1 raised to n plus k can be written as minus 1 raised to n into minus 1 raised to k. Since minus 1 raised to n is free from the parameter k, that can be treated as constant, that can be taken outside the summation, that becomes minus 1 raised to n. Rest of the things, summation k varies from 0 to infinity, and here we left out minus 1 raised to k, and this k factorial I have written as it is, this one, and this n plus k factorial. And already we have taken use of one particular result from gamma functions, that is gamma n plus 1 can be written in terms of factorial. Means gamma function can be written in terms of factorial by subtracting 1 and putting the factorial sign for that one. And again, this factorial can be converted in terms of gamma by adding 1 and putting that one in the gamma sign when n is a positive integer. Again, we can write this n plus 1 factorial can be written in terms of gamma of n plus k plus 1 according to this result. And this one x by 2 raised to, and this becomes what, 2n minus n, that becomes n, that is 2 into k, that is 2k, because this one we have written according to this using gamma n plus 1 equal to n factorial. And this minus 1 is taken out, that is already, that is minus 1 raised to n. And this is, again, this results an expression for jnx. Just earlier, if you take equation 1 in the previous problem, there you have taken r as a parameter, but in the place of r, we are having here it as k. Again, this will be an expression for jnx. That's why we have put that j minus n of x equals to minus 1 raised to n into jnx. That will be the second property. These two are very important properties of Bessel's function. Now let us go with some examples on this Bessel's function. And the first example is, prove that j half of x equals to root of 2 divided by pi x into sin x. And this can be easily be proved by taking n equal to 1 by 2 in jnx. Now let us see how it flows. We know that jnx equals to summation r varies from 0 to infinity minus 1 raised to r divided by r factorial into gamma of n plus r plus 1 into x by 2 raised to n plus 2r. And once you take n equal to 1 by 2, we are going to get this one. And now this x by 2 raised to 1 by 2 plus 2r can be written as x by 2 raised to 1 by 2 into x by 2 raised to 2r. And that x by 2 raised to 1 by 2 is taken out. then this summation r varies from 0 to infinity. This is minus 1 raised to r. This is r factorial, and this is r plus 1 by 2 plus 1. That becomes 3 by 2. Then this x by 2 raised to 2r is written as it is. Now, this x by 2 raised to half means that is root of x by 2. Now, let us expand this summation by taking r equal to 0, 1, 2, 3 and so on. Once you take r equal to 0, minus 1 raised to 0 is 1, 0 factorial is 1, and this is once you take r equal to 0, you will get gamma 3 by 2 that you have written here, and this x by 2 raised to 0, that is 1. Now the next value r equal to 1. If I take r equal to 1, that becomes minus 1 raised to n, that is minus sign. Then if we take r equal to 1, that becomes 1 factorial. If we take r equal to 1, that becomes gamma 1 plus 3 by 2, that is 5 by 2. Then this becomes x by 2 raised to, if we take r equal to 1, that becomes x square. Plus 1 upon, if we take 2, minus 1 raised to 2 is plus 1. If we take r equal to 2, it becomes 2 factorial. If we take r equal to 2 here, 2 into 2, that is 4 plus 3, that becomes gamma 7 by 2. And this is x by 2 raised to 4 and so on. And again, we know one important result from recurrence relation of gamma functions. That is, gamma, when n is not an integer, gamma n can be written as n minus 1 into gamma n minus 1. Now let us apply this rule for each of the gamma functions, gamma numbers which are available in the denominator. Using this result, let us see what happens to the above result. This root of x by 2 can be written as root x by root 2, and this is 1 upon this gamma 3 by 2. If you take n equal to 3 by 2 here, that is 3 by 2 minus 1, that is 1 by 2 into gamma 1 by 2, I can write minus, and this 1 factorial is 1. And for this, if I apply that one here, if I take n equal to 5 by 2, I'll get 3 by 2 into gamma 3 by 2. 3 by 2 are written as it is. Again, that gamma 3 by 2 can be written as 1 by 2 into gamma 1 by 2. Again, applying the same rule. Then into x square by 2 square, that I can write, plus 1 upon 2 factorial is 2. And for this one, if I go on apply this result successively, I can write first time it is 5 by 2 into gamma 5 by 2. That gamma 5 by 2 can be written as 3 by 2 to gamma 3 by 2. Again, that gamma 3 by 2 can be written as gamma 1 by 2 to gamma 1 by 2 to x raised to 4 divided by 2 raised to 4 we can write. And once we observe each term of the denominator, I can take 1 upon 1 by 2 gamma 1 by 2 as common. Therefore, we have taken common. Then we left out 1 here. Since this is taken out, okay, here we left out 2 ones means here 4 is there. 1, 2 will get cancelled. Here we left 2, 2 into 3. That becomes 6. That we get x square by 6. And it is plus. And since 1 by 2 into gamma 1 by 2 is taken out, okay, then here this 2 will get cancelled. And here it is 2 raised to 4 means 16, and 1 2 will get cancelled. That is 1 2 will get cancelled. That is 8. 8 into 5, that is 40. 40 into 3, that is 120 we get. Now, in order to put this one in the standard format, we will multiply by x and divide by x, and this is an adjustment factor, what we call. And now this is root x by root 2, and denominator of denominator, this 2 will go to the numerator. And again, from gamma function property, gamma half is root pi. That's why in the place of gamma half, we have written root pi. Now, denominator x, you keep that one here as it is, and numerator x, we take inside the bracket. Once you multiply 1 into x, that is x, x square into x, x cube, x raised to 4 into x, x raised to 5, and so on we get. And this x, if you take the simplification among these two, this is root x and this is x. 1 root x will get cancelled, so we left root x in the denominator. And out of these two, 1 root 2 will get cancelled, so root 2 we left in the numerator. Then this is root 2, the simplification of these two. The simplification of this and this results in root x, and this root pi are written as it is. Now this is x minus x cubed by 3 factorial. And because 6 is 3 factorial, 120 is 5 factorial. That becomes x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial and so on. And this is the series expansion for sin x. That's why, since all are in terms of root, we can write them in a single rule, that is root of 2 divided by pi pi x into sin x, because this is an expression, that is power series expression for sin x. That will be sin x equals to, that is x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial, and so on. And here the important fact we have to note that we are using two important results of gamma. One is gamma n equal to n minus 1 into gamma n minus 1, and gamma half is root pi. And this is the adjustment in order to put this flower bracket in terms of some standard function as sin x. They are the things we have to keep in mind. That will be the first problem on that Bessel's function. A similar example, earlier we have proved an expression for j half of x. Now let us prove an expression for j minus half of x. And again we have to prove that j minus half of x equals to root of 2 divided by pi x into cos x. And we know that an expression for j and x is this one. Wherever n is there, let us take n equal to minus 1 by 2 in this case. Now this becomes r varies from 0 to infinity, minus 1 raised to r factorial. If I take n equal to minus 1 by 2, minus 1 by 2 plus 1, plus 1, that becomes 1 by 2. And r as it is, this is x by 2 raised to minus 1 by 2 plus 2r. And again, this x by 2 raised to minus 1 by 2 plus 2r can be written as x by 2 raised to minus 1 by 2 into x by 2 raised to 2r. This x by 2 raised to minus 1 by 2 is free from r. I will take it outside. Then let us take the value for r equal to 0, 1, 2, and so on. When you take r equal to 0, this becomes 1, this becomes 1, and this becomes gamma half. And when you take r equal to 1, that becomes minus. This becomes 1 factorial, this becomes gamma 3 by 2, and this becomes okay, this becomes, once you take this one outside, that is, once this is taken out, once you take r equal to 1, that becomes x by 2 raised to 2 plus 1 upon 2 factorial. Once you take 2 here, this becomes 5 by 2, and once you take r equal to 2, that is x by 2 raised to 4, and so on. And again, we can apply the same rule what we have said in the above expression or above example, that is gamma n can be written as n minus 1 into gamma n minus 1. Now let us apply the things which are here. This is gamma 3 by 2, gamma 5 by 2. Let us apply this result for each of those. This one, raised to 1 by 2, raised to minus 1 by 2 means 1 upon root x by 2 is there. Then this is as it is, and 1 factor is 1, and gamma 3 by 2. Using this, it can be written as 1 by 2 into gamma 1 by 2. And this is x squared divided by 2 raised to 4. Plus, this is 1 upon 2 factorial is 2. And for this gamma 5 by 2, if you apply this rule successively, first time this gamma 5 by 2 can be written as 3 by 2 to gamma 3 by 2. Once again, if I apply the same rule for gamma 3 by 2, it can be applied as written as 1 by 2 to gamma 1 by 2. And this is x raised to 4 upon 2 raised to 4. And once you observe the denominator carefully, from each denominator I can take gamma 1 by 2 common, and I can write like this. And let us know this one as, this is 1 upon root x by 2. This can be written as root x divided by root 2. Denominator of the denominator, that root 2 will go to the numerator. That becomes root x divided by, root 2 divided by root x. Since gamma half is taken out, and here we left out 1. And since gamma half is taken out, 1, 2 will get cancelled. That becomes x squared by 2 plus gamma half is taken out. Okay, this 4 will, this 2 will get cancelled. This is 2 ones are 2, this becomes 16. That is 8 into 3, that is 24, and so on. And now this is gamma half is root pi, and this is x minus x square divided by 2 means 2 factorial, 24 means 4 factorial, and so on. Since by combining all these, we can write them in a single root as root of 2 divided by pi x. And again, this is an expression for the series expansion of cos x as a power series of x. That's why we know that the power series expression for cos x is 1 minus x squared by 2 factorial plus x raised to 4 by 4 factorial, and so on. That's why this can be replaced by cos x. That's why we have proved that j minus half of x equals to root of 2 divided by pi x into cos x. That will be the second example. And these two examples, that is an expression for j half like root of 2 divided by pi x into sin x, and j minus half of x is root of 2 divided by pi x into cos x. They are very, very important examples. Once we refer the previous question papers, many of the times one will be there in the exam. That's why try to practice these problems. And one more last example, let us go with this. Now, that is, we are required to prove that d by dx of x raised to n into j n x equal to x raised to n into j n minus 1x. That will be the expression we are required to prove. Now, by the definition of j n x, we have this one. And now let us multiply both sides by x raised to n. That becomes LHS x raised to n into j n x. Summation r varies from 0 to infinity. And this one minus 1 raised to r divided by r factorial gamma n plus r plus 1 we kept as it is. Now, before multiplying, this can be written as x raised to n plus 2r. Once you multiply once again by x raised to n, base is same. By adding the powers, it results as x raised to 2n plus 2r. And this one, if you take the power, that becomes n raised to, 2 raised to n plus 2r. On multiplying both sides by x raised to n, we get this one. Now, this expression has to be differentiated with respect to x. Now, differentiating both sides with respect to x, we get this one, our constants, we kept as it is. This is also constant, we held as it is. Now, this, if you differentiate using the rule, derivative of x raised to n is n into x raised to n minus 1. That is, keep the power front and subtract 1 from the power. We can write this one. Then this is r varies from 0 to infinity minus 1 raised to r. This is r factorial. And again, using the result that gamma n plus 1 can be written as n factorial, or we can say gamma n plus 1 can, or gamma n can be written as, because we have used this one many of the times, gamma n can be written as n minus 1 into gamma n minus 1. That's why this result can be written as n plus r into gamma n plus r. Out of these, you take 2 common. Then we get n plus r. Then here, this x raised to 2n plus 2r minus 1 can be written as x raised to n into x raised to n plus 2r minus 1, because base is same. By adding the powers, we get the numerator. And again, this 2 raised to n plus 2r can be written as 2 into 2 raised to n plus 2r minus 1. Then this n plus r will get cancels. This 2 will get cancels. And this x raised to n is free from the parameter r. That's why we can take that one outside the summation. Okay, because as we have written here also, that is this one can be written like this using the result gamma n plus 1 into n, gamma n plus 1 equals to n into gamma n. Now take that x raised to n, which is free from r. Then we left summation r varies from 0 to infinity. That is minus 1 raised to r divided by r factorial into, this is n plus r. Then this is taken out by combining these two, because both are having the same powers. It can be written as x by 2 raised to n plus 2r minus 1. Now the same thing, this is x raised to n. This is as it is. This is as it is. Then this n plus r can be written as n minus 1 plus r plus 1, because plus 1 minus 1 will get cancelled straight up with the previous step. And this one can be written as n minus 1 plus 2r. And once you look at this expression, this is an expression for jnx, just n is replaced by n minus 1. That's right, we can write it as j n minus 1x, because once you look at this expression, this will give an expression for jnx. Once you look at this, just in the place of n, we are having n minus 1. That's why we can write it as j n minus 1x. Therefore, this will be the required result, that d by dx of x raised to n into jnx is given by x raised to n into j n minus 1 of x. That will be the required result. And now one simple practice problem I would like to say, that is prove that integration from 0 to pi by 2 root x into j half of 2x into dx equals to 1 by root pi. Just I would like to give a hint for this. Consider Jnx. Consider Jnx. Wherever n is there, you take 1 by 2. Otherwise, we can, that process goes lengthy. Otherwise, we already proved that an expression for j half of x. We know that j half of x is root of, okay, j half of x is root of 2 divided by pi x into sin x. And here, wherever x is there, you take 2x. Then whatever you get, you multiply that one by root x. And whatever the resulting is going to be there, you integrate that one with respect to x between the limits, that is 0 to pi by 2. Definitely it results in the value that is 1 divided by root pi. Try to work out this one by considering the expression for j half of x as root of 2 divided by pi x into sin x, and by replacing x by 2x. Try to work out that one. Thank you.